Now let's talk about Ampere's law. So here is the integral form of Ampere's law. The line integral of a beam along the line is mu naught by the, and also with the circle or the circumference inside of the area, how much current flowing through this area. But for the purpose of this class, we only dealing with a symmetric. Actually, this equation might only works for symmetric J. So if we have a symmetric J, we can just simplify it to equation without integral. B dot L equals to mu naught dot In. Basically, that's like how much the current bundle into that area. So this, for instance, there's a current flowing that way. You can know that you basically think of you're holding this current, and your thumb is pointing at the current direction, and your four other fingers are pointing at the direction of your B field. Basically, that is the right hand rule. Let's think about three different scenarios. First, let's think about like a wire. There's a wire, and then we want to know the B field of a radius r. So we know that the circumference of a circle is 2 pi r, and within inside of the circle we only have a current I, and also the whole setup is symmetric. Then we have that, basically we get the B out of this. So B equals to mu naught I over 2 pi r. So what if we want to know the current flowing within the wire, like that, which I'm pretty sure you guys already encountered in the lecture or some quizzes in the lecture. So we want to know that at radius small r. So if we assume that the current density is uniform across the wire, so we know that the circumference is 2 pi small r, and the area is pi r squared. So the current within will be J dot pi r squared. So J dot S with I within. That's pretty much I within J dot pi r squared. So using that, we will getting the B field within the wire, and that one is a little bit harder to comprehend, but I'm pretty sure you guys can handle that. There's a solenoid, and we have a wire running around it like n times. To apply Ampere's law, we have to get a really big line around there, so that we know that there's no B field way around here, like here. So like this solenoid, that's a B field of solenoid. Like it's almost concentrated at the center, but like if you have the line way far away from there, so there's barely any B field. So you can just know that you can just think there's only B field inside of the solenoid. So we get B dot L equals to n pi I, and that is a really useful formula for calculating the B field, because a lot of configuration is solenoid, and also those will happen in the future, and also I'm pretty sure that will happen in your quiz on the lecture class instead of the lab. I don't know, but yeah.